I do a lot of data warehousing stuff. So I actually have about 2 hours of material here. So I'm going to cover some things, and I'm going to skip some other things. So I want to see who's in the room so I can decide what to skip. So how many of you actually have been building or trying to build data warehouses on Postgres? Okay. And how many of you have built data warehouses on other database management systems? And how many of you have heard of this data warehousing thing and think it's probably going to be part of your job but aren't quite sure how to get started? Okay. So we got the experienced people here. So I will be zooming through a lot of the introductory material here and going straight to some of the techniques, and particularly how they apply to Postgres. So I'm not going to get into hardware. Not going to get into backups of large databases because these things take a fair amount of time to cover by themselves. One thing, just to get absolutely clear what I'm talking about when I say data warehousing, there's been a lot of throwing words around about this. There's been a lot of throwing words around about this thing called big data. Like other media buzzword terms, it's inherently lacking in specific meaning. Big data can refer to data warehousing. It can also refer to very large transactional workloads, you know, a la Dynamo, Amazon, Instagram, that sort of thing. So zoom through some stuff. So in terms of what I'm going to be talking about for data warehousing is specifically, classically your data warehouse is you have one or more business processes or data collection devices or user interactive things that produce data. Sometimes it's a side effect of what they primarily do. And that data gets accumulated in database storage in order to produce some sort of intelligence or reports about the organization. And you know, you keep accumulating data and you keep accumulating data and you keep accumulating data until you've got really a whole lot of data and a lot of problems managing it. So again, in terms of big data, I'm going to be talking about the data warehousing end of things, where we're accumulating a lot of data in order to run a relatively small number of very large user requests. Now one thing I do think is worth covering, even if people have experience with data warehousing, is the three primary kinds of data warehousing. If you are doing data warehousing at all, you're going to be doing one of these three, or possibly two of these three at the same time. One of the first, which is my favorite, which is actually sort of a recent arrival, is this archiving concept, where the idea is that you are accumulating data frequently because you are required to accumulate data for regulatory reasons or for security reasons. But you don't really have specific needs to actually use that data. This is what I call WARN, for write once, read never. And I've worked on a few of these, and they have very specific performance characteristics. And generally, when you're working on an archiving database, your goal is the most efficient storage possible, because you're trying to limit the cost of a database that you don't expect to query. The second type is what we call data mining. And data mining starts with, gee, our sales system, our website, our weblogs, whatever, produce a whole lot of data. I'm sure there's something valuable in there somewhere. I'm sure there's a pony in the bottom of the shit bucket. And I want you to find it for me. So the idea is you're going to be accumulating a whole lot of data, a lot of which is, from the perspective of the data engineer, garbage, hence semi-structured data. That is, you have some data in there that's valuable, and you have a whole lot of garbage in there that's not valuable, and you need to separate out the two. These sorts of data warehouses tend to be very, very large, and you're really aiming there to maximize your ability to do CPU-intensive processing in order to search for the valuable data. The third kind actually goes under a variety of different names depending on whose products you're looking at, but they all mean the same thing. Business intelligence, decision support, OLAP, which is a specific technological approach, but you hear it applied to the entire realm, and analytics are the most common terms used. Now, what these all mean in a summary is, I want to produce really slick-looking reports so that management can make decisions based on this huge amount of data that we have. And for these sorts of databases, you really, usually the data is a little bit smaller than it would be for, like, say, data mining. The data, the form of the data, the structure of the data is relatively well understood. Often it consists entirely of taxonomies and numbers. And primarily your whole data warehousing strategy is going to be around indexing and materialized views and other ways to pre-digest the data so that you can produce reports quickly. So, now there's a couple of, I want to also zoom through this. People have, with some experience for this, but I do want to actually mention a couple things because there's some misunderstanding about the terms dimensions. The basic idea of a dimension here is you've got a fact table, you have any number of other bits of information about your main body of data that actually fit within a universal structure of ideas about data. So it could be geography, could be a taxonomy, could be a structure within the organization. Just about anything can be a dimension. Where a lot of people get into, and there's also, for some of the newer databases, they're coming up with new names for the term dimension, like facet, taxonomy, secondary index, view, which depending on the product also simply mean dimension. For example, the Lucene family uses facet instead of dimension. This is where a lot of people get confused when building data warehouses. A dimension is not a surrogate key. I cannot count the number of times I say, oh yeah, well we built this and we imported this and then we normalized it by giving everything integer IDs. In what way is that related to normalization? You give things integer IDs for storage efficiency, and only for storage efficiency. That's the only reason to do it. For example, this is a cut-down table from one data warehouse that I work on that happens to be publicly on GitHub, so I can talk about it, where these are crash reports from Firefox. And now, people tend to recognize that these things, which actually have been giving integer IDs and relate to another table somewhere else, in this case product version because it relates to a whole hierarchy of products and versions and releases. Signature and flash version because those tend to be very long strings, so I'm doing that for storage efficiency. And people tend to recognize those as dimensions, but the thing is, these things are also dimensions. Even though, in other cases, you make these decisions, you say, look, operating system name is actually a very short string. There's only a few of them. It doesn't really gain me a lot to export that to another table and then write an integer ID back in its place. And it does help me to be able to actually just query that directly on the fact table in terms of having a simpler and then often much more often correct query plan. And similar with other stuff. I mean, usually if your data is really well understood, most of the stuff in your largest tables in a data warehouse are going to be references to dimensions, but that doesn't mean they need to be big integer surrogate keys. A couple of other terms people may be familiar with. Star schema. This is when you have usually a single gigantic table and a bunch of dimensions around it. And that's what's called the star schema. For a more complex data warehouse, you can have what's called the snowflake schema, where you have several very large tables which have some kind of relationship to each other. And again, they do it because of the shape of the sort of diagram. Snowflake schema databases are harder to optimize because you have to do these joins between gigantic tables that may or may not be partitioned. So a couple of things. Believe it or not, in the data warehousing stuff I do for clients, I don't always use mainstream open source PostgreSQL because it's not always the right tool. Sometimes it is the right tool, more often than a lot of people would think, but it's not always the right tool. So one thing that Postgres is good for, like other multi-purpose relational databases, but particularly Postgres, is that it can do everything. Maybe not the most efficiently, maybe not at the largest scale, but if you want to do archiving or data mining or analytics, or even do transaction processing and analytics on your database at the same time, Postgres can do that. Whereas more specialty products tend to be able to do only one thing. Postgres also has surprisingly good support for complex queries. This is another one from an actual data warehouse in production. The actual query goes down to about the carpet level. And when I started optimizing this query, it was actually running in 60 seconds. So we have a very good query planner. It can handle these things that you throw at it just, right away. I'll be getting into some of the more complex types of queries that are actually useful in this talk. So Postgres is really good for that. What we're not necessarily great at is when you get up to really large sizes. A few other things, and I'll talk about these. Partitioning table spaces, point-in-time recovery is for backup. I'm not going to talk about that. Same with binary replication, resource control. And I added this one when I actually realized I started working with Hadoop, which has no resource control. So you'd better be sure you know how much memory the queries, the MR jobs you're going to run are going to take, because Hadoop will happily let you run the entire cluster out of memory. And it didn't occur to me this was a big feature, but it actually is, because a lot of the newer big data databases don't have any resource control. Another big thing for Postgres is extensibility, particularly the ability to take analytical libraries and inject them into the database. So things like R, like some of the Perl genotype libraries, like a bunch of other stuff. Another really good thing about Postgres is, as you can see from being in this room, a lot of people are already running a lot of data and doing data warehousing stuff on Postgres. So when you get stuck, you can hop on, say, the PostgreSQL performance mailing list and actually get help, and get help from other people who face the same problems that you have. So when would I not use Postgres for data warehousing? Well, the biggest thing is actually size. Which is Postgres has some limitations in how it deals with data. The biggest one of which being that we don't yet have parallel query. That limits the effective size of limits the comfortable size of a data warehouse in Postgres. Generally, I find when I get over about 10 terabytes, it starts getting fairly painful to run your database on mainstream, your data warehouse in mainstream Postgres. There are exceptions to that. Stuff in the archiving class, for example, seems to be able to take any size because you're not querying it. But in general, when somebody says to me, oh, I've got 16 terabytes, I've got 25 terabytes, data for this, I start looking at more specialty products. Whereas I've had other people come to me and say, well, we want to evaluate Greenplum, that sort of thing. I'm like, how much data do you have? Oh, 900 gigabytes. I'm like, why are you bothering? Just use Postgres. It's license free. It's easy to understand. It'll work. And by the way, in the specialty products we're talking about is some of these data warehousing specialty databases, Vertica, Greenplum, Netezza, et cetera, a lot of which actually are based on Postgres. A bunch of them are Postgres forks. Some of them even have, like Lucid, have compatibility with Postgres. So it can be an easy leap to one of these if your data gets much, much larger in size. So now for some of the more technical stuff here, having whizzed through the background material, configuring Postgres for data warehousing. So most of the configuration and setup advice you'll find online in general about PostgreSQL will be for transaction processing and web applications, because that's what the majority of people are doing. And you don't want to set things up exactly the same when you're doing a data warehouse. So first thing, latest version of PostgreSQL, particularly if you're doing a data warehouse now, you want to be using 9.2 because, anybody give me a reason? What? Yeah, index-only scans. That's the killer 9.2 feature for people in the data warehousing set. The multi-CPU thing really applies to a concurrent transactional workload, which you don't care about. because you're only going to have 2 or 3 requests running simultaneously. You really care about index-only scans because that makes covering indexes possible and that sort of thing. So in order to eliminate I/O-bound queries, you want as many drives as you can get your boss or company or whatever to put in a budget for. If you can get them to put in a budget for SSDs or NVRAM, Fusion I/O, Viridiant, even better. The SSDs, et cetera, are portrayed as being fast for transactional workloads and stuff, but frankly, in my experience, I found if you can get ones that are big enough, they're much better for data warehousing because they're really nice on index lookups, which you're doing all the time. It's also very important, like a transaction workload, to put a very large write-ahead log, your PGX log, and put it in a separate drive because you're going to be doing large data imports, which are going to be writing gigabytes of data to the database at once. And you want those to spool out in the transaction log, get flushed out of memory, and then spool back. You don't want to be recycling the transaction log a whole bunch of times while you're trying to do a bulk load. This is the biggest thing, though. The biggest thing is if you are getting into serious performance data warehousing territory, do not have the data warehouse be the same server as the server that's running your public website or your business application, because the transactional workload and the data warehousing workload have very different profiles. If nothing else, user queries tend to conflict. It'd be nothing like having your website go all 400 errors on everybody because somebody's running a massive reporting query and using all of the hardware resources on the server. So get a second server for your data warehouse if you don't already have one. Some basic settings. Again, low concurrency workload. You might want to enforce that in case somebody has a bad script that runs out of control. So low max connections. You actually, compared to transaction processing, you actually tend to have a lower shared buffers on current Postgres for a data warehousing workload because you want to maximize the amount of space available to the file system cache. So if I had, say, 64 gigabytes of RAM on a data warehousing server, for a transaction workload, I might give it 8 to 12 gigabytes for shared buffers. For data warehousing workload, it would be more like 4 to 8. So I want to offer more room for the file system cache. You're going to want to have the individual resource limits be very high. Work memory, maintenance work memory, temporary buffers, which is the size of a temp table you can construct before it spills to disk. And this is why it's important to enforce low concurrency in your workload because, you're allowing users to use, 11 gigabytes of memory just for one query. But if you have the memory and there's only one user in the system at the time, you should allow them to use that amount of memory. The wall buffers advice is just standard for all Postgres installations and automatic on 9.1 or later. So this is one of the areas, auto vacuum is one of the areas where it gets really different from transaction workloads because if you have a transactional workload, you would never turn auto vacuum off. You might modify its behavior, you might change some settings, you might turn it off for individual tables, but you wouldn't turn it off in general. For data warehousing, it's standard to turn it off. Auto vacuum has a really annoying habit of kicking in the middle of a large multi-step bulk load. So instead, you want to do your vacuuming as part of your data import process, whatever that is. Or, on a calendar so that you can be sure it's not happening at the same time that you're trying to modify hundreds of gigabytes of data. Also, the other way you eliminate auto vacuuming is that you use partitioning in order to rotate your tables instead of vacuuming them. So, a few Postgres features that are useful for data warehousing. Table spaces. How many people here are actually using separately defined table spaces in there? Okay, fair amount. So you already you know what this is about. So the basic, for those of you who aren't, the idea is that a table space allows you to take a portion of the database and target it at a specific storage resource. So and it's actually fairly simple. Postgres even takes care of moving the data for you. Although if that's a terabyte table, it can take a while and use a lot of I/O. Well, it does, but you don't have to add extra commands. And the main reason, there's two main reasons. Number one, you can use table spaces to expand your available storage if you don't have the ability to increase the share that the data warehouse is already on. If you have to add new volumes, that are separately named, then you can just add table spaces and move individual objects over to that. The bigger reason is in order to parallelize access. So for example, anytime you're writing an indexed row and you're writing the index values, the row and the indexes, if Postgres could write them simultaneously, it would. And so if the table's on one table space and the index is on a different table space, then Postgres can do a certain amount of parallelization between those just based on the I/O system. Now, all of this is not, that sort of parallelization is not particularly useful in comparison to having a high-end SAN direct-to-storage attached storage device that often does a lot of the same activity at the hardware layer. But if you are using less expensive storage, like individual drives, dumb attached storage that you need to attach to your device itself, this can be a big benefit. One of the big benefits is actually to establish one or more separate temporary table spaces. So in Postgres 9.0 and later, I think, you can actually specifically assign the temp table space not just to a specific table space, but to more than one specific table space, and Postgres will actually use the pool of table spaces you've assigned it rotationally. And if your workload involves doing a lot of on-disk sorts, as data warehousing tends to do, this can be a very large performance benefit if you have the disk resources for it. This is a little bit of instructions on moving your temp table space. And actually, and this is one of the areas where, again, and really, at this time when SSDs and Fusion I/O cards are getting affordable, but not affordable enough to, say, put 8 terabytes of data on, this is something you can really take advantage of, and you can say, hey, this data is super critical. This is my temp table space. I'm going to put it on these SSDs, even though everything else is on older relational storage. ETL. This was actually the reason why I originally wrote this talk, because I went into a site and I was talking to a bunch of developers, and we were setting up a data collection apparatus for several terabytes worth of user activity information. And I said, well, so explain the ETL process you're currently using. And they were, the what? ETL, extract, transform, load, complete blank look. And these are people who were in there to talk to me about using, Postgres or Greenplum or Hadoop or Vertica, or, about to spend, $500,000, $1 million on data warehousing technology. Didn't know the terminology. So, terminology, for those of you who don't know this, extract, transform, load. And all it is how do I get from my raw data or from my source data into the form that it's going to be stored long-term in the data warehouse. So from web logs to an analytics database, from point and sale files to financial reporting database, from an OLTP server to your archival data warehouse. It's also called ELT when when, as is common these days, the transformation of the data happens inside the database. Postgres is particularly good at this because of the number of tools it gives you for transformations. So, loading. There's always insert, obviously. A lot of people like insert. Problem with insert is that it tends to be fairly slow if what you're inserting is millions of rows. Batch stuff up in transactions if you can, because if you do one row at a time, then each row is its own individual transaction. That takes forever. So batch things up into like, a few thousand rows or whatever. This is what third-party tools that are not specific to Postgres tend to do, in a lot of the Java stuff. But you have to recognize that it's slower than other approaches that you can take. One of the other things that you might want to do if you have to use insert because of your tools or because of your data, try to come up with a way to insert more than one stream at a time, because Postgres can take that, even more so as of 9.2, and it'll speed things up a lot. Now, if you are doing something native to Postgres, your much better interface for loading is copy. So our own internal bulk loading format, what we use for backup and restore, tends to be 3 to 5 times faster than inserting in terms of the number of loads, because it's got a fast path for the parse and the load. Drawback is not fault tolerant at all. So copy a million rows, run into one bad row, whole thing gets thrown out, transaction error, and you have to start over. Actually, this is called, oops, I forgot, this is called PG Bulk Loader now. There are some tools that help you with the fault tolerant thing, like PG Bulk Loader. The drawback to PG Bulk Loader is that it's slower, because it's actually batching stuff behind the scenes so that it can roll back. Little copy syntax. One of the nice things is, for the last number of versions, people didn't know about this, you can copy from really any delimited file. With the CSV stuff, you can name your delimiter, you can name your row end or whatever, which means that you can often go directly from whatever's outputting your data into Postgres without needing an intermediate loading tool, which can be very convenient. Now, as of 9.1 and later, we have another option for loading, which is foreign data wrappers. So the idea here is, instead of writing stuff to a file, then copying it into Postgres, you tell Postgres to open a client connection and attach directly to the source of the data, whether the source of the data is a file somewhere else, or whether the source of data is maybe another database server. And then you go directly into the transform process in order to get into the final tables. That skips a whole step and substitutes network bandwidth for I/O, but because you're skipping several steps of writing things and then reading them, it can often be much faster. As an example here, just a simple CSV file example, you take a CSV delimited log file, you create a CSV data source, and then you can start running queries directly against it, which is really valuable if you only wanted a small portion of the log to begin with. Because you're storing a lot of duplicate data that you're just going to delete as part of the transform process. Transforming, temporary tables. I do a lot of work with temporary tables when you're doing a data transformation. That's why increasing the temp buffer setting is so important. People know about this on-commit drop thing. So one of the things you can do when you create a temporary table in Postgres is create it inside a transaction, tell Postgres on-commit drop, and then you don't have to remember to delete it later and have your ETL process fail if you have to rerun it because it was interrupted. Big change in here, though, unlogged tables. So a lot of the reason for using temporary tables for doing these transformations is the contents were disposable, and you didn't want to double write them to the transaction log when they were just an intermediate stage of your data. But the problem is that if you lose your session, if the database shuts down, you lose the temporary table, and you have to start the process back over from the beginning. And if it was an 11-step process, you might not want to do that. Well, now we have a different option, which is unlogged tables, where it's a permanent table, but it's not written to the transaction log. Now, that does mean if you have an unexpected database shutdown, you lose the contents of the table. But if you don't have an unexpected shutdown and something interrupts your ETL on the client end, the table's still there, and you can start where you left off. So that's very valuable. Now, the other big thing for transformation in Postgres that's really useful is doing stored procedure. By running your analytics and transformation code much closer to the data, it can be much more efficient. You can sometimes even get some parallelism out of it that way. So you can really write your stored procedures in almost anything you want to. You can write, actually, functions in SQL that are very useful for transformation stuff. PL/PG/SQL is the most common, but people write stuff in PL/Perl, PL/Python, PL/PHP. One of the biggest ones for doing data warehousing type stuff is PLR. Let me give you a couple examples of that. How many people here have seen the pgfouine log digest thing? Yeah, so before they released PG Badger, which I'm now using, I actually was starting to rewrite pgfouine as an inside the database stored procedure-based thing. So I took the pgfouine query, the pgfouine query normalization code that removes the constants, added some other cleanup stuff on it, and I went ahead and put it in a Perl procedure in the database as an example of using the power of something like Perl, which is excellent at regex-based text manipulation, inside the database instead of outside the database. This one is actually an old example from Helene of using PLR. And this one's particularly fun because this particular piece of R code, which is running over a weblog, doesn't produce a table, it produces a graph, which you could then actually store in a byte A field as a way of pre-calculating reports. More frequently, I use PLR for things like doing medians and quartiles, things that are a little bit annoying to do in SQL, and R is actually very good with. So, some tips on ELT. If you can, for your initial data import step, if you are doing an import and not doing foreign data wrappers, bulk insert into a brand new table instead of inserting into an existing table. It's much, much faster. You do it in one transaction. It's even faster because it doesn't get logged whether it's an unlogged table or not. When you're doing gradual cleanup of data, try to update all the columns in each row at once instead of one at a time, because Postgres is row-based storage, so every time you update a column, there's going to be some version of the entire row. So you've got like 40 columns, you update them one at a time, you've actually got 40 versions of every row. Not good behavior. Use views and custom functions to simplify your queries. This has no real performance impact. Postgres rewrites those behind the scenes as part of the rewriter step. But it makes your code much more maintainable because, you're not at every step looking at a query this big. You're looking at a few references to other routines that you're calling. And it makes your code much more maintainable. And as part of your ETL procedure, the insert into the long-term tables should be your very last step. You don't want to insert into your long-term storage tables and then do a bunch of cleanup on it. Among other things, that makes your long-term tables require a lot more vacuuming. So do all of your transformation in temporary tables, unlogged tables, whatever, and then bulk insert it into the long-term storage and you're done. So, windowing queries. This is, as an SQL geek, this is like one of my favorite SQL features for doing analytics in the database. Now, with a regular aggregate, what happens is you condense the data, right? You've got your key, and you're going to summarize in the value, and you end up with less rows than you started with often. The problem with that is that if you want to correlate between the individual row and the aggregate that it's part of, you have to do a self-join, which on a large set of data tends to be fairly expensive. So what windowing queries allow you to do is you can go through the rows in some order and say, for the last 3 rows, for the rows in this group, give me the total and then put that with the row. And that way you can actually compare the total. Like, for example, you can, in one pass, say, what percentage is this of the total? Which is something people want to know all the time. Some more specific examples here. So, say, for example, here's a very common thing. I want the top 3, so this is from the Socorro project, which I like to use because it's public and open source. I want the top 3 versions of Firefox that were by the number of hang crashes, that's when it freezes on you, by the number of hang crashes that were sent in on September 5th. And that's a very easy query, right? Order by, the report count limit 3, right? Simple. Here's the problem, though. What if I want the top 3 for each day for a week? How do I do that in one query? Well, Before windowing queries, generally what you did was you wrote a script and you ran this for each day, which is annoying. But with windowing queries, this is a little bit more complicated looking. So I'm talking about back useful complicated queries, right? It's a little bit more complicated looking, but I can do it in one query, and in one query that's surprisingly fast. So the important thing here is this is our windowing thing. So what I say here, oh, and by the way, I'm using common table expressions, or as I like to call them, with clauses, because it always starts with with, right? You put, and this makes it more maintainable, I put my whole window in this common table expression, and then I tell it what I want to do. So we're going to have a row number, which is an arbitrary incrementing number for the row. And then I want to actually group it by the day and order it by the number of crash reports. And then I take every one where that row number is 3 or less. And then you end up with something like this. And that's in one pass and without having to do an iterative loop over your data. This can get much more complex. For example, this is a windowing query that we're actually using in production in Socorro. And what this does is it takes a whole bunch of pre-digested materialized view crash data, and here's our windowing thing right here, which is in the middle of it, which is actually using dense rank and a couple of other things to figure out relative position of a particular crash signature. And what it results in is this. And you can actually see it a lot better if you go to crashstats.mozilla.com. A very sophisticated report showing all kinds of relative things of how different kinds of crashes are going up or down in frequency, which the Mozilla developers use to make Firefox less crashy. So the basic idea of windowing queries is you're doing stream processing on SQL. So if any of you are familiar with SED, with other stream processing libraries, that's what you're doing. And stream processing is great on really large data because it means that however large the data is, you're going into it on one end and going out on the other end. What gets really expensive with large data is correlation. Anytime you have to say, take this gigantic body of data and match it against this other gigantic body of data, you're going to pay a high price in terms of execution time and required resources. Anytime you can say, take this gigantic body of data, start at the beginning, go to the end, and give me a result when you're done, it's going to be much faster. And a windowing query approach helps you do that. Partitioning, big important issue for data warehouses. If you're going to have a multi-terabyte database, you're going to be partitioning some of your tables. So Postgres partitioning is, I have to admit, describe it as Postgres partitioning is just good enough for no one to feel compelled to implement better partitioning. It's based on table inheritance, which was originally developed for a different purpose, and this principle called constraint exclusion. So the basic idea is that each partition is actually created as a separate table, and it has all the characteristics of a separate table, but it's inherited from a master table. And importantly, you have one or more check constraints on the table. So for example, we have the master table here, which will be empty. And then you actually create inheritance with check constraints to define the range of that particular partition. The system has the advantage of being very flexible. It has the disadvantage of being very labor intensive on the part of the DBA, either manually or in the form of writing a lot of scripts. Plus, Postgres does not automatically decide which partition to write into on its own. So you need to do that in some other way. The most efficient way is if you can actually do it in the middleware, that if the middleware can have consciousness of the partitioning and write to the correct partition. A slightly less efficient way, but one you often have to pursue because the middleware does not understand partitioning, is to use like triggers. One little hint there, by the way, if you're using time-based partitions, you only care about the three most, the 2 or 3 most recent time-based partitions. Because if somebody's inserting into data from 3 years ago now, then there's probably some other kind of problem with your data. So you don't actually want to do that on an automated basis. This is an example of an insert trigger. Partitioning is good for a number of things. Number one, biggest thing it's good for is quote-unquote rolling off data. That is, you have a mandate, we're going to keep 5 years of sales data, and so every quarter you want to delete the quarter from 5 1/4 years ago. Well, deleting 100 million rows out of a billion row table, or out of a 10 billion row table, is a very expensive operation and may not complete in any time that your staff is willing to put up with. On the other hand, deleting a partition is merely unlinking a file. Takes seconds, if that. So it's excellent, it's indispensable for that on large tables. It's good for maintenance, too, because vacuum tends to be more efficient over smaller tables than it is over gigantic tables, and involve less locking. It's excellent for queries which are going to be on the partition key because they have to scan less actual data. Our particular implementation, really doesn't go up above a couple hundred partitions. And it's actually good for insert performance because because B-tree indexes lose efficiency as they get very large because of the number of levels in the tree. So what it's bad for is all of the extra administration you have to do to maintain the partitions. Queries that don't use the partition key, and this is true of all forms of partitioning, are going to be slower. It's terrible for joins between the partition table and, say, another partition table, or another table but not on the partition key. Constraint exclusion tends to function very badly over a couple hundred partitions because of the amount of time that Postgres takes checking all of the constraints. And update performance, if it's not on the partition key, also tends to suffer. Most important thing about this, though, and by the way, this is sort of an aside. So a lot of people are already doing data warehousing stuff. How many of you have a written data expiration policy for your data warehouse? Wow. So this should be job number one when you go back to the office. You need a data expiration policy. Storage has gotten a lot cheaper than it used to be, but it's still not free. And the database gets harder to maintain and harder to work with and more expensive to support the bigger it gets at some degree. This is going to take a lot of meetings. People don't like to talk about deleting data, but you don't want to get, but eventually you'll end up with a policy like this. And it should be differentiated policy, So you have things like, okay, well, the raw import data we'll keep for a month, and detail level transactions for 3 years, and the detail level web logs for 1 year, and the roll-ups, the summary tables and stuff for 10 years. So, materialized views. I'm going to run out of time. Okay. So, materialized views are another indispensable technique. We don't have specific tool support for them in Postgres, but that doesn't mean you can't still use the technique, because all a materialized view really is the query results as a table. The idea is, if you have a summary of a very large amount of data that you are running repeatedly, that is the foundation for a lot of other stuff you're going to do in the database, then you should run that summary once and store it. This isn't necessarily going to be a query in the final form of what you want to output. It's much better if it's actually foundational data, doing, say, some of the more expensive parts in terms of time, of other queries that you're going to do. We don't have AutoMagic materialized view support in Postgres yet. Kevin Grittner is working on it. So we'll have it at some point in the future, maybe 9.4. In theory for 9.3, but since I haven't seen any patches yet, I'm thinking 9.4 is more likely. But you can still do this manually. So here's a good example of this. So say in this very simplified example, I'm constantly looking at the total number of hits per page out of a weblog. And then I'm actually calculating a bunch of stuff up and down into that, by subdomain, by geo, by other things. Well, it might be good to actually, rather than calculating against the raw weblog all the time, to actually have a summary per page for the week, actually as a table. So if this is the query that I'm going to run, then I might take this, create a table called page hits that has the page and the day and the total hits. And then on a cron job, every day add into this a total. And then when I actually want to look at some more nuanced version of that, it's a much faster query, orders of magnitude faster. So this step can be done in the middle of the night when nobody's actually looking at the data, so that this step that's being done interactively can be much, much faster. If you're maintaining, because you have to do this manually, because we don't have automatic magic support, for maintaining mat views, the best way to do it is, again, this becomes part of a data load process. If you have a defined data load process where you're copying data over to Postgres on an hourly basis, on a daily basis, on a weekly basis, whatever, then updating the mat views should happen as part of that process. If your data is coming into the data warehouse continuously, then it should be chronologically based. You have things that fire off every hour that update the summaries or whatever. I do a lot of this, in implementation. What's a really bad idea for a large database, for a data warehouse, is having triggers that automatically update the materialized views. Because those triggers are going to basically fire on a per row basis. And when you have 80 billion rows, it's a very bad idea. Some tips. If you find your mat views ballooning to be 10 times larger than RAM, then you've probably done something wrong, because they're not really going to help you a lot in terms of performance over the raw data. When usually the reason that happens is because you're using a single mat view for too many different things. You should look at breaking it up into several separate smaller mat views that each serve one purpose. On the other hand, where you can keep them small, mat views should serve more than one purpose so that you're not having a lot of duplicate storage. Also, as much as possible, you shouldn't be updating mat views. You should be inserting or truncating and reinserting depending on the nature of the view. Also, these are for reporting, so index them like crazy. So, last topic here, I'll talk about a little bit briefly. EAV, another term that I throw at a lot of newer, database people that I run into that they haven't actually heard this abbreviation before. That stands for entity attribute value. And the idea is the entity is your key, your ID. An attribute is some kind of attribute class, and a value is some kind of a value. And where you run into this is in a lot of cases where the data structure is not known at the time you construct the data warehouse for a variety of reasons. To give you an example, so I'm building this big data warehouse for wind turbine information. And initially we start looking at just constructing regular tables, So for every tick, which is actually a second, because we get new data every second, you're going to have the turbine in the second. We're going to have a bunch of values like its power output and wind speed and relative facing and production mode, gearbox, and whether or not it's faulting or in curtailment, that sort of thing. There's actually about 700 of these facts. The problem is that the actual list of facts varies by manufacturer, and by site, and by age, and by who set up and configured the individual turbine. So it's not possible at the time that we install this data collection device, it's not possible for us to know what our actual list of facts is going to be. So we have to take a more generic approach. So the approach we're taking is actually more nuanced than this, but it's very similar to, you got the turbine and the tick, you have an attribute ID that references an attributes table, and then you have values of different types that you can actually store in there. The advantage of this approach is that it means that you can decide what your attributes are at runtime, and you can change them also. Somebody adds a new sensor to the turbine, we can just, add one line to the attributes table and it's there. You don't have to store missing attributes, so if the majority of your attributes are missing for the majority of your rows, the majority of your entities, then there's no storage, and you can sort of write very generic code and reuse it. The disadvantages are mainly storage and efficiency related. First of all, in Postgres, again, row-based database, we've got 14 bytes of row overhead, plus however big the key is, which in this case is, I don't know, what's 16 bytes, I think, actually. So however big the key is. You can't enforce constraints really meaningfully except by like trigger or stored procedure code that you really don't want to be running over, millions of rows per second. Combining attributes, queries that actually have to combine several attributes. Show me everything where this is this, and this is not that, and this is between this and that, and this has 3 of those. Those tend to be really, really expensive because you're doing this enormous self-join. And the big thing is, you think about this, is you've thrown away most of the power of the relational database because you've taken away the knowledge of what's being stored away from the database engine. And you pay a pretty heavy price for that. So there's some alternatives to this, most of which fall under the heading of eblob, as we call it. So you can use arrays. Postgres has built-in arrays support, so sometimes arrays work positionally. HStore works very well for generic text values, particularly in cases where most of your values are missing. Our new JSON support, which makes a lot of sense if the data you have coming in is JSON. Or if you've got some sort of binary data, you can even stick it in a byte A field or whatever, that sort of thing. The disadvantage of eblob is, every time you retrieve any of the data, you're retrieving all of the data. It's one big field. The database is going to decompress it, send it back to you all at once. The other thing is that a lot of people don't consider as a serious alternative is to actually just use columns. You can actually add columns at runtime. Postgres supports transactional DDL. It's actually not a completely out-of-the-question approach if you have a way of detecting the new attributes as they come into the database and adding the column. You can also use an approach we call sparse columns, where you have this huge grid of 700 columns, but for any given row, most of them are null because it only takes 1 bit to store a null in a Postgres row. So again, this is actually a viable approach, and in fact, when we were doing the wind farm thing, these were approaches we evaluated. We tested to see which one of these made the most sense for the particular application. And it very well could have shaken out to the row approach. The main drawback of the just use columns is that when you get over to thousands of columns, you get some pathological behaviors in the Postgres planner. And particularly, you can never do \d table name in PSQL. It will break on you. So I'm actually out of time. I had a little bit about cubes here, but we're going to actually skip that. So in fact, I'm going to skip to the last slide so that we can actually do some Q&A. I know I wouldn't get through all of this. So questions? Nobody has any questions about data warehousing in Postgres? I don't know. Are you working on it? There's been a lot of talk about it. The problem is that we don't have any hackers really actively working on it. I think the best solution is to attack it piecemeal. So start out with parallel sort, which I think is the most easily isolated portion, and then move up to other things. There was another one over here. That's what PG dump is for. The government will obligate you to keep the data, but they don't obligate you to keep it in the database. Okay, but you can still have a second, because this is actually a case where you sometimes end up with more than one, because there you basically have 2 different purposes, right? You have the data warehouse that's maybe doing analytics that you're using actively, and then you have the second archiving purpose that can be a much lower performance data warehouse, but possibly much larger. So one of the approaches you can actually take there is you copy the partitions, as they enter that time window of being archived, but you're not allowed to throw them away. And, using PG dump or foreign data wrappers or something else, you copy those partitions from the analytics warehouse to the archiving warehouse. Or you just buy a lot more storage for the archiving warehouse, for the analytics warehouse. It can even be useful if you're running different kinds of reports to simply detach it from the parent table, so break the inheritance, so it's not being included in the analytics queries that you want to run for your purposes, but is still available to the database for the government stuff. I mean, the problem with the government stuff is There's a lot of requirements around it, but they're actually unlikely to access it ever. So you're looking for, how can I fulfill the letter of the law in terms of response time without devoting any more resources to it at all? Much. Based on the single pass principle. I mean, actually, in general, this not only applies to windowing functions, but in general, when you're running a query over big tables, you really want to think of, how can I do this in a single pass through the table? You do a lot of nested queries, where you say, this query is going to produce a result, and this outer query is going to do an operation only on that result. I'm not going to correlate it against anything else. I'm not going to join the subquery against something. I'm just going to do something on that stream, and then maybe have another outer query that's actually doing something on the stream produced by the inner query. And that turns out to be very, very efficient. It ends up being more or less, at close to the maximum speed at which you can read the table, as opposed to any form of correlation, like say a join between two subqueries or doing a loop or something that where you're doing a lot of random lookups. Any more questions? Yeah, actually. So I had a few tool slides. I wasn't going to go into them in detail because, again, that's its own talk. But these are all things that I have used with Postgres at one point or another. So I know they all work. Obviously, the open source ones are going to tend to have better support for Postgres than the proprietary ones. But these are all multi-database tools, and these days multi-database means it includes Postgres. Is it a good idea to use foreign tables in what? Okay, so the question was, is it a good idea to use foreign tables against another Postgres database? Not yet. I mean, you can use it with dblink just in a strict data import sense. Not yet. One of the hopefully big features for 9.3 will be full federated database support, at which point this will, among other things, it will become a way to get ad hoc parallel query, because you'll be able to, the system will push down portions of the query, so not just lookups, but even joins onto the external database. And then it'll become a very useful technique for data warehousing. Right now, it's not. Okay, I think we're actually out of time. I'm pretty sure there's another, is there another speaker here? Yep. So thank you very much.